We're now going to talk about inequalities that allow us to bound tail probabilities with moments like the mean, the variance, higher moments, and the moment generating function. These are incredibly important inequalities, and for example, we use one of these when we prove the weak law of large numbers. The first inequality that we're going to look at is called Markov's inequality. And here, if we have a positive random variable, so this is a random variable that is greater than or equal to 0 with probability equal to 1, with a bounded mean, a bounded expectation, then we can bound the tail probability of this random variable, the probability the random variable is greater than or equal to epsilon, by its mean, the expectation of the random variable, divided by epsilon. One thing to note here, because our random variable is positive, we don't have absolute values anywhere here. At first glance, this inequality might seem not incredibly useful. However, it's going to be a workhorse inequality, and we'll see that we can transform lots of other questions to appear in this form. Now we're going to prove this inequality. The proof is actually quite straightforward, not too much work. So let's choose an arbitrary epsilon greater than 0. So let epsilon greater than 0 be given. And now we would like to show that that probabilistic statement holds. So we can write the probability that z is greater than or equal to epsilon. And this is just going to be the integral from epsilon to infinity of, I'm going to write it as 1. I don't need this 1. We'll see why I have this later, times the density of z dz. And just to note, this also holds for discrete random variables. Here I'm just going to do the proof for continuous random variables. So we're going to note a fact, and we noted this in another calculation for bounding tail probabilities of Gaussian random variables. And that is, if we have a value z that is greater than or equal to epsilon, then we note that that means that z divided by epsilon is greater than or equal to 1. And since the whole integrand in here is always positive, or at least non-negative, if we replace 1 by a value larger, in this case z over epsilon, we will only increase the value of the integral. We will not decrease the value of the integral. So this is a relatively common trick and actually quite important. Let's scroll down a little bit. So I can say that this integral is now less than or equal to the integral from epsilon to infinity. Now I replace 1 by z over epsilon times this density of z dz. And now, again, since this quantity is always non-negative, I can change this bound of integration. Rather than integrating from 0 to infinity, I can, epsilon to infinity, I can integrate from 0 to infinity. And that will only increase the value of the integral, or at least not decrease the value. So this is z over epsilon pz dz. And we know that z only takes on values between 0 and infinity. So I can move this epsilon out because of linearity of the integral. And then this whole thing is just going to equal the expectation of z divided by epsilon, completing the proof. Just as a reminder, really the workhorse here was replacing 1 by something that was greater than or equal to 1, and this moved us from an integral of a probability to an integral that looked more like an expectation. The next inequality that we're going to look at is Chebyshev's inequality. Now we have a random variable z that doesn't have to be positive, it's just distributed on the real numbers. For this random variable, we require that its variance is less than infinity. And if that is the case, for any epsilon greater than 0, we can bound this tail probability, this probability of z being further than epsilon from its expectation and absolute value, by the ratio of the variance, sigma squared, divided by epsilon squared. Right? So now we've moved from taking a positive random variable and bounding its tail probability in terms of its mean to a not necessarily positive random variable and bounding how far it is from its mean in terms of its variance. And we'll see Chebyshev's inequality is relatively straightforward to prove using Markov's inequality. Chebyshev's inequality was one of the critical components that we used when proving the weak law of large numbers. So to prove this, we are going to choose an arbitrary epsilon greater than 0. Then we are going to define a random variable w. So we're going to let w be defined as z minus its expectation squared. And I could have put absolute values here rather than parentheses. We'll see, because I'm squaring things, it doesn't actually matter. So w is now a positive random variable. All right, so the first thing we're going to do to engage with w is we're going to rewrite this probabilistic statement that we would like to bound. And we are going to square both sides of the inside. So this is going to be equal to the probability that z minus expectation of z quantity squared is greater than or equal to epsilon squared. And that is precisely equal to the probability that w is greater than or equal to epsilon squared. And now, from Markov's inequality, we have that this is less than or equal to the expectation of w over epsilon squared. Right? And the expectation of w is just sigma squared. So we have this is less than or equal to sigma squared over epsilon squared, and this completes our proof. Right? So this was quite straightforward using Markov's inequality. The general strategy we took here was we defined a positive random variable, in this case, one that is quite related to the variance, and we related the tail probability we cared about to the tail probability of this new random variable whose expectation we understand, because its expectation is in fact the variance. We can also apply Markov's inequality with moments other than just the second moment. Here, if we consider the central kth moment, so we look at the expectation of z minus its mean in absolute value to the kth power, and if we assume that that's less than infinity, then we have an inequality that looks a lot like Chebyshev's inequality, except now, rather than our bound being the variance divided by epsilon squared, it's this central absolute kth moment divided by epsilon to the k. And the proof follows almost exactly like it did for Chebyshev's inequality. Right? All that we end up doing is now we define our random variable w to be equal to the absolute value of z minus the expectation of z to the k. Right? And now we can reframe that probabilistic statement. Maybe I'll just work through that. The probability that z minus its expectation in absolute value is greater than or equal to epsilon. Well, take both sides to the kth power. So this is just equal to the probability that w is greater than or equal to epsilon to the k, which now, applying Markov's, is less than or equal to the expectation of w, which is gamma k, divided by epsilon to the k. Right? And probably I should have written this more formally, but that completes our proof. More generally, what this result tells us is that if a distribution has a higher order moment, then its tails fall off more sharply. In particular, if this kth order moment is finite for a distribution, then we know that the tails fall off at least at the rate of a polynomial of order k. As a final application of Markov's inequality, we have what's sometimes called exponential Markov's inequality, or sometimes called generic Chernoff inequality. And here, if we have a random variable z with some distribution on R, and its moment generating function exists for some value t greater than 0, here t is sort of a parameter that we can play with in our moment generating function, then we have a tail inequality. This is a right-sided tail inequality that involves the moment generating function in the numerator at that value t, and gives us an exponential bound to the tail in the denominator. So just as a reminder, existence of the moment generating function is a stronger condition than existence of any of these lower order moments. And showing that a tail decreases at an exponential rate is stronger than showing that a tail decreases at any polynomial rate. All right, so to show this, we use the same strategy as before. We say, okay, we could now define maybe w equals e to the tz. This is going to be our positive random variable. Note that that's always positive, whose expectation is the moment generating function. And again, we can say the probability that z is greater than or equal to epsilon equals the probability that e to the tz is greater than or equal to e to the t epsilon. And then applying Markov's inequality, we have that this is less than or equal to that moment generating function divided by e to the tz. Right, and now we're done. I only looked at a right-sided tail inequality, right, looking at the probability z is greater than or equal to epsilon. You can form a similar inequality looking at the probability z is less than or equal to epsilon, only for that result, you end up with t less than 0, but the proof follows almost exactly as this proof did.